There we go. All right. Today we're going to talk about DataStax Enterprise and Akka systems for scalable, fault-tolerant applications. My name is Aaron Standard. I'm the co-founder and CTO of a company here in LA called Hadoop. And I'm also the co-founder of the Akka.net project, which we'll talk a bit about in our presentation. So what do we love about DataStax Enterprise? This talk's about 20 minutes long, and I'm going to leave about 10 minutes for questions afterwards. So we're going to touch on a lot of conceptual stuff. So think of your questions. So what do we love about DataStax Enterprise? My previous company was Marked Up Analytics, and there we go, got some Marked Up fans back there. And we used DSC in production for 2 years. And here's the things I really loved about DataStax as a business owner and an architect. I love the intuitive programming model, CQL3. Raise your hand if you've ever done relational database programming before. Yeah. I would say that SQL is about as ubiquitous a language as JavaScript. Everyone's worked with it. And yeah, sure, there's some differences in terms of how you model stuff in Cassandra versus MySQL. But the overall model is pretty familiar. And on top of that, DataStax provides Dev Center, which is a great tool for testing and developing all of your SQL queries and schema. The other thing that really attracts people to Cassandra, and it certainly attracted us, being an analytics company, is how easily you can distribute data and partition it in clusters. So, another show of hands. How many of you have ever had to write a sharding or partitioning client for a relational system? Alright, you guys are my brothers and sisters. You feel my pain. You understand how awful and terrible it is. In Cassandra, I can go and connect to any one of these nodes, write one copy of the data, and then save 2 replicas anywhere else in the cluster. So if I kill one or more of these nodes, I'm still going to be okay. And because of how consistent hashing works, I don't need to care which node my app connected to and need to write which piece of data. The coordinator in Cassandra is going to figure all that out for me. It's easy mode. I like the fact that Cassandra is highly available. So not only does it have great availability within one ring, where it's able to provide 3 physical copies of data, but it's even aware of things like which racks replicas are hosted in, or which availability is on Amazon. And you can even easily set up replication to totally different data centers thousands of miles away from each other. So the fact that Cassandra makes this really easy and intuitive to do is magical, quite frankly. Did I mention that DataStax has an awesome conference swag? It's one of the things that, I don't know if they're handing out anything this cool today, but so far the mug and the t-shirt I've gotten have been very cool. So always appreciate that. They do events really well. And more. One of the things that's great about the drivers that DataStax does for Cassandra is the fact that they have auto-discovery built into them. You can go ahead and remove a node or add new ones, and your application will automatically be informed that, hey, there's new nodes in your ring that are available to accept writes and reads. And the fact that you can change your network topology independent of how your application was initially deployed is pretty amazing. The fact that you have tunable consistency in Cassandra is really important. That you can read with a different level of consistency than your writes. Being an analytics company, we had to hand off the write as fast as we could in order to keep serving requests. But when a customer wanted to read a data, and we basically did, I think, 1 write for every 15 to 20,000, especially 1 read for every 15 to 20,000 writes, that read needed to be at a much higher level of consistency. So being able to set that made a really big difference for the responsiveness of our app. The tremendous read-write throughput. I'm not going to mention the company by name, but I had a friend who worked at a big social app company that uses Cassandra here in LA. And he mentioned they pushed a version of their iOS client that accidentally doubled the number of calls they made, write operations specifically, to their Cassandra cluster. And they didn't notice for 4 weeks in production, even though they had millions of active users. Just because Cassandra's ability to handle that write throughput was pretty amazing. And then there's the DataStax Enterprise Startup Program. If you're an early stage company and you're looking at using Cassandra, you can get access to it for free as long as you're under some certain fundraising and revenue thresholds. You should chase down Patrick McFadden if you can find him again later. So my talk today is really about all this great stuff that we like about DataStax Enterprise. What if we could have that in our applications we build ourselves too? What am I talking about? The intuitive programming model that allows you to build highly available, reliable apps that can be deployed independent from your network topology. So not having to, every time you want to go and add a new node to a microservice, you don't have to go and push config files or redeploy anything else. How many of you can easily do all of these today with your current tools? Raise your hand. I see a couple of brethren back there who I assume are probably using the actor model. I'm going to use the stupid Fabio joke at least 2 more times in this presentation, so I apologize in advance. Enter the actor model. So what is it? The actor model was, like any brilliant technology, was invented in the 1970s. Specifically, it was first implemented in Erlang, and it's been used successfully in big applications like WhatsApp and Live Nation, not Live Nation, Go.io and others. And it's been ported to a number of other languages. There's the Akka framework in Java, and there's Akka.net, which Bridge, what we do is provide commercial support for this. And I'm one of the core contributors for all the clustering and networking stuff that we do. So, mandatory social proof slide for any technical decision makers in the audience. These are some of the companies that are using the JVM flavor of Akka in production. That includes Twitter, LinkedIn, a number of others. It's a proven technology that's being used under some pretty massive loads today. So, what the hell is the actor model? First, everything is an actor. The actor model is as different to object-oriented programming as object-oriented programming is different to old-school C-style procedural programming. Everything in your application is an actor. And so this is what an actor looks like. So this is a basic untyped actor, which is the most commonly used type of actor in Akka. And everything I'm showing in these slides, by the way, even though this is C#, is equally applicable to the Java and Scala sort of implementation of Akka. So, and all the Java JVM folks in the room here should still be able to get value out of it. So this is it. This is all that it needs to do. It has one little method that receives messages and has a message handling code. What's that about? Well, the way actors work is they pass each other messages. There are no method calls. You don't do invocations on an actor. You send an actor a message. And then an actor, just like how a human being could, can do a little bit of work and send a message back. Or maybe go and send messages to other actors too. Here's an example of message passing in action using the Akka implementation. So you have actor 2 and actor 1. And why do they have little addresses down at the bottom there? Well, that's because every time you send a message, you don't push the message directly into another actor's on receive loop. You send a message to an address. And the actual framework, the Akka framework, will route it to that address. So in this case, we're literally sending a string to users as actor 1. And at this point, actor 2 is free to continue asynchronously doing whatever else it needs to do, responding to other messages. And actor 1 will eventually process this message. All messages are processed by default in sort of first in, first out order. Actor 1 will go and receive that message and maybe do some work. Try to decide how to respond. Maybe it'll go and check the content of the message and see if it needs to talk to an external data store or anything else. Whatever. It could be whatever you want. And then it will send a response back. In this case, as I put it very eloquently, sub-home dog is what it will say back to the sender's address. So actors send messages to addresses. This is what a sample, fully articulated Akka address looks like. It's pretty similar to a URI. And these addresses are guaranteed to be globally unique. Even if you had a million machines with a million actors all running as part of one clustered actor system, every single one of those individual actors would have a unique, distinguishable address that you could use to route messages to it from anywhere in the cluster. So this is a really important concept, thinking about how you actually do distributed actor systems. So here's an example using some more C# code. I talked to my actor system, which is a little part of the built-in wiring built into Akka.net. And I'm going to say, can you get me a handle for the actor of this path? This is like a relative path, so actor addresses also have the notion of relative versus absolute paths. I'm going to say, yeah, I want to talk to the console reader. And you might get a selection back if there is an actor at that address. And you can send it a message. So you really communicate to actors by asking for a reference or a handle on that actor, and you send messages to it. And you can look up those handles by address. So where I'm going with this is that actors have a property called location transparency. Does anyone know what that is off the top of their head? Raise your hand. Alright, well, location transparency is a concept that you actually use every day. If I call my co-founder Andrew, where is he? You back there? Yeah, he's back. If he's in Boston and I'm in Los Angeles and I dial his cell phone number, I don't need to tell AT&T, hey, can you hop my phone call from this cell tower to that backbone connection to that cell tower to Andrew? No. I just need his cell phone number and AT&T will do that routing work for me. So that means that when you get a handle on an actor, it might be a handle for an actor that's on a remote machine 1,000 miles away, or an actor that is sitting adjacent to you in memory in the same process. It looks exactly the same to you as an application program. There is no difference. Might be a little bit of difference when you're asking for an address in the actor system. Hey, can you be a handle for this path? But other than that, you send a message to it. Once you have a reference, you can send a message anywhere. And this has one really powerful implication for how actors can work at scale. This is the magical scaling sauce, people. It's what makes everything, well, actually, the real word is high availability. Alright? I get a little carried away sometimes. So high availability, with location transparency and the fact that actors can send messages transparently to other actors running inside the same process, or distributed actors running on other machines, means we can do stuff like this. I can go ahead and have one actor send a message to another. That actor might reply to two other actors that can be hosted on the same process or a different machine. And they can go ahead and have this sort of chatty sort of conversations across the network or across in-memory message queues. The way you design this as an application developer is exactly the same as if this actor system is running in one process versus running on the network. How you deploy and route messages is a configuration detail, not something you need to build into the architecture or design of your application. So let me talk a little bit more about that. So scaling out, actors can be deployed anywhere. You create an actor in Akka using what's called a props, because every actor needs a props, right? It took me like a year and a half to figure out why they were called that. Actors can be deployed anywhere. You can use props to serialize the formula for being able to create and instantiate an actor anywhere. So if I have machine A and machine B that are hosted in totally different data centers, I can send props over the network and say, hey, create an actor of this type at this address. Machine B will create it, and it will send a remote actor reference back to me. And so, well, how do you take advantage of this and scale out? Because you can use special types of actors called routers to distribute work. You've probably heard a little bit about consistent hash distributions today. Raise your hand if you've heard that in the previous talk. So that's how Cassandra is able to route messages over the network. You can use that exact same strategy with routers. Routers can go and create actors and guarantee there's going to be at least 2 instances of this type of actor per machine in your cluster, and they can route messages to it using a number of different strategies, like round robin or consistent hashing. And that's really how you're able to take advantage of scale out via configuration. And the last bit is actors are cheap. You can fit 2.5 billion actors into 1 gig of RAM. So that means that restarting or redeploying or killing or reusing or fanning out with actors is really inexpensive. So you can deploy them and use them anywhere. They're a disposable resource. So you can form highly available systems using this. Let's say we're using the Akka cluster module, and I can go ahead and describe 3 different microservices that make up my application. And they all know about each other via a gossip protocol, exactly like Cassandra. Well, if I want to bring a second replica of one of these services up in a different data center, it can join and form a cluster and begin gossiping the availability of each of the nodes in that particular cluster. It works exactly like how Cassandra does, using the exact same programming model. And so with automatic clustering, it uses the same approaches you use for scaling out a Cassandra cluster. You specify some well-known seed nodes, and that gets baked into your configuration whenever you deploy a new machine that has your Akka cluster running on it. New nodes can join and leave at will. So if you have auto-scaling turned on, or if you have you need to go and deploy a new version of an app, those nodes can join and leave independent of all the others. And they'll be notified via the gossip protocol who's up, who's not, who's available to do work. And then work can automatically get redistributed because routers. If you're using routers to try to push information in this distributed way across the cluster, it can automatically respond to these changes in network topology and deploy additional actors on new nodes and rebuild killed actors that were on machines that left the cluster. So this is a really powerful concept. And that's not all. The other things that you get with Akka and Akka.NET are persistent actors. Actors that automatically persist their state in some durable store via an event sourcing model. So if you have an actor that needs to, I don't know, let's say you need to have a level of transactional consistency in your system. If you're a big e-commerce company and your order fulfillment system is running on top of actors, making sure that actor's message actually was made it from point A to point B is pretty mission critical. Otherwise, you're going to have a lot of really upset customers. So persistent actors give you the ability to guarantee reliable delivery and a number of other important features for those high consistency settings. And the other thing that actors allow is cluster sharding. So in Cassandra, when you set a replication factor of 3, Cassandra is going to guarantee that you have at least 3 physical copies of that data somewhere in the node at any given time. What you can do with cluster sharding is do that for your application state too. You might have one primary instance of an actor running on one machine that is responsible for doing all the work. But all the while it's doing its job, it's going to broadcast its state to 2 standby replicas on physically different machines in the cluster. So you have a piece of mission-critical state. Let's say you're using Akka.NET as a session store. You can have that state backed up to a persistent store like Cassandra and have hot replicas of that standing by in the event that machine goes off the network, or that actor dies, or that process fails, or whatever. So this gives you a really good high availability store. And there's also other stuff built into Akka, like being able to guarantee a singleton instance of an actor in a cluster. So if you have a scheduler actor, for instance, you can make sure there's only one of them. And a lot of other fun stuff, too. So DataStax Enterprise plus actor systems. With our powers combined, we can bring an end to this. Actually, wait, are there any Disney people in the audience? Okay, cool. I didn't want to get sued if I kept talking. So, actually, let's move on to this one. So you might already be using actor systems in combination with Cassandra if you're a DSE user. Because Apache Spark is built on top of it. All of the streaming capabilities that Spark has are built on top of the JVM version of Akka. So you can go, at least in the current version that's out now. So you can take a look under the hood and see all the different Akka packages they're using for clustering and reliable delivery and so forth. And so what we're talking about today is really how you can combine the actor framework itself to do all sorts of powerful combinations with Cassandra. So for instance, stream processing. One of the things that people like using Storm and Spark for is being able to aggregate and accumulate data as it's entering your cluster. But what if you could react to that data as you're streaming it? Imagine if you needed to send a push notification to someone using your mobile app that, hey, there's XYZ available. Or maybe fire off an alert if you're building an Internet of Things application built on top of Cassandra. You can intercept messages on their way to your Cassandra cluster, keep a little bit of state in memory for each individual stream, and then react, push something back out into the real world. This is what we used Akka for and marked up, was the ability to build marketing automation on top of our analytics engine. Be able to push messages that our app developer customers would specify down to their users. Other things you can use it for is event sourcing. We also did this at marked up. So let's say you needed to maintain state for a million different state machines for figuring out whether or not a user is eligible for this coupon or discount or whatever. Being able to build that on top of Akka.NET and Cassandra is pretty easy. All you have to do is just use the built-in persistence module. And that'll take care of it for you. But what about real-time aggregation and analytics? What if you need to be able to do something that Storm or Spark can't easily do out of the box? So for instance, being able to go and build a real-time recommendation system using unsupervised machine learning. Well, Akka gives you a very atomizable, sort of really small code footprint way of being able to build that in. Essentially, it's a do-it-yourself stream processing framework that's really easy to program against and can scale out pretty largely. And then lastly, who here works in e-commerce? Quick show of hands. All right. How much fun is it working with stuff like dynamic pricing or dynamic product recommendations and personalization? Or even better, when you have a large number of customers and a very small amount of inventory, like if you're Ticketmaster trying to sell out a Bruce Springsteen concert. We're dealing with issues that deal with serializing requests. Akka and the actor model provides a really powerful way of doing that. You can basically add a level of almost transactional consistency on top of Cassandra before you figure out whether or not a piece of inventory is still actually there or not when you sold it. So that's some of the problems that people are using Akka for in production today. And I think that's about it for my spoken content. So if you have any questions about Akka and Akka.net, go ahead and reach out to us at Pettibridge. Honestly, we're not here to try to make money off of consulting. We just want to see more people using Akka and Akka.net in production. And the other thing that we specialize in is helping .NET companies be successful with Cassandra. So if you're doing anything on the Windows stack and have questions, please ask us. All right, I think I've got